In this series of videos, we will consider waves. Waves are an extremely important part of physics. Half of the world can be explained in terms of particles, and the other half requires us to use wave mechanics. Waves are extremely important to understand the nature of light. It's also important to understand even the nature of electrons or atoms themselves, since their wave properties can determine how they react in what is called quantum mechanics. So in order to do waves, and we're going to study these, you need a precise definition, but this would require us to have calculus. So instead, what we're going to do is we're going to make a qualitative definition of waves that will work for us for now, and we'll begin by studying the properties of mechanical waves. These are waves that go through various types of mediums such as water or a string, and they are more familiar to us. So the first thing we'll do is give a qualitative definition of wave rather than a mathematical one. And it says that the definition of a wave is the propagation of a disturbance without the transfer of matter. So we're going to look at disturbing something and watch that disturbance get propagated through the medium. But we're going to need to note that no matter is actually propagated with this disturbance. An example of that is take a pond or something and drop a pebble in the middle. Pretty soon you'll see that there are little ripples, and a ripple will look something like a circle, and over time that ripple will move further and further and further out in bigger and bigger and bigger circles, at least something like that, if you would. The water that was actually at this location did not move out to here. This water bumped into other water molecules, and the disturbance that was started here, the slapping of the surface, created a peak, and that peak has moved out. That disturbance has moved outward in all directions, like this, in all directions. But the actual water molecules themselves did not move with it. They have stayed where they're at. So there is no transfer of matter, but there is a propagation of this disturbance, this peak. This is just one of many examples of waves, but the key point is that is the propagation of the disturbance without the transfer of matter. Now, although matter doesn't get transferred, some other important things do get transferred. For instance, energy gets transferred. The energy that was applied by the stone or pebble when it hit the pond gets moved out and eventually becomes this wave out here that can hit the shore. Obviously, a water wave smashing against a building or a shore can erode or destroy the shore. Also, linear momentum is transferred. We can get energy and linear momentum when sound waves are sent to us. It is the linear momentum that is applied a change to our eardrum that therefore we say change in linear momentum or change in time implies a force. And that force does work on the eardrum and we gain energy. And that energy we call sound. So these two concepts, linear momentum and energy, can be transferred without the actual original water molecules moving all the way out to the shore and striking it. Now, most mechanical waves are due to a series of linked oscillators, so there's a direct connection to the stuff we studied about oscillators and to this stuff in waves. An oscillator particle, say right here, oscillates back and forth because it was disturbed. Maybe you pulled it this way and let it go, and it went back and forth, back and forth. And if there was just one oscillator, that's all there would be. But what's different now is that we've hooked other oscillators to the first oscillator. So when this oscillator gets pushed over this way, he shoves this oscillator, which shoves that oscillator, which shoves this oscillator, which shoves this oscillator, which propagates the disturbance all the way over here. This oscillator here did not get transferred all the way over to this far wall. But the shift in this person caused all these other oscillators to be propagated down until the disturbance ends up here. So each oscillator stays oscillating back and forth about its equilibrium position. But the disturbance, when you disturb one, will propagate from one oscillator to the other all the way across propagating the disturbance through the medium. A propagation of a disturbance without the motion of matter. All right, without the propagation of matter. Now, I want to look at a video of another type of oscillator now, and that's an oscillator involving a set of metal rods. And I want you to watch carefully in this video. And in the video, you'll see a set of metal rods, and each one of those rods represents an oscillator. And they'll be oscillating up and down because the person's hand will move them up and down. Each of those oscillators will not move horizontally, only up and down. But the disturbance will propagate horizontally. No propagation of matter, but there is a propagation of the disturbance. Watch the video. Another common wave besides just a wave pulse is what is called a sinusoidal wave. This occurs that instead of having a single disturbance, we have some sort of periodic disturbance, such as something that's beating on the water repeatedly, or something that's pulsing our little metal wave machine at a fixed rate. When these oscillators undergo periodic motion, if they're driven in a periodic period, up and down, and what we get is a wave that's both periodic in time and periodic in space. So at any one time, there will actually be multiple peaks that you can see, and the distance between those peaks is called the wavelength. In fact, it doesn't have to be the peak. It can be any similar point on the wave. So if you were to take, for instance, a specific picture at a specific time, you will see this distance between them at a single instant of time, and we call that distance the wavelength. I will show you that in a video now. Hopefully in the video you notice that the individual rods only go up and down still, but the propagation is shown to exist throughout space and not to be localized at one point. So in fact the idea of a position vector makes no sense in talking about waves because waves are spread out through space. Let's consider an example of this in the case of a boat on an ocean. So here's my boat, and at the moment it happens to be on one of the peaks. There is a distance between these peaks. I could take a photograph at a single instant of time, and I could see that there is some periodicity here between this going across that length in space. And in fact, I could measure that to be some distance. On the other hand, if I was to watch over time, I would see the boat go down and then the boat come back up. The distance that the boat went from its highest to its middle point is still the amplitude, because the boat in essence is on a piece of water that's undergoing periodic motion like a harmonic oscillator. So from there to there is A, and down to this trough is minus the amplitude. The time it takes to go up from there, if I was to use a stopwatch and watch only the boat, not the sideways, but just the boat, would be called the period, T. So the time it takes boat to go up and down is the period. And we still have that the angular frequency times the period is 2 pi. It's just a harmonic oscillator. But we now have this spatial picture in which there's multiple peaks. And we know that what happens is, as the boat's going up and down, this disturbance is moving horizontally over with some speed. This is interesting, and we can actually note some things about it. First of all, we've indicated that there's a distance over which it will repeat itself. That's called the wave number, the wavelength. The distance between two similar points. They don't have to be a peak. They could be the distance between two troughs. So you could measure from here to there. You would get exactly the same value for the wavelength. You could measure from where it starts going up to where it starts going up. That distance would also be the wavelength lambda. In addition to the wavelength, there was something similar to what the angular frequency is. This thing looks like a sine or cosine, and it's repetitious with 2 pi. So there is a number of waves in a given distance, in the same way you could have a number of waves in a given period of time. So this time, k times lambda is equal to 2 pi, rather than omega t, and this k is called the wave number. Now, we'll not find the wave number to be as useful in this course, but it's in fact often more useful in upper level classes than is the wavelength. The reason is there's a connection between k and linear momentum, and there's a connection between k and some other things in advanced math called Fourier analysis. Now, I said that a wave doesn't seem to be located at a point like a particle, and it makes no sense to talk about the position vector. So how are we going to describe this idea of a wave? How are we going to tell you where the wave is if it makes no sense to talk about the wave at a point if it's spread out? Well, you kind of know that when you look at pebbles. When you drop the pebble in the water, what you saw moving was the peaks. These were points of constant phase. That may have been when the sine or cosine was a maximum. And you watched how that maximum moved through space over time. So this idea of constant phase fronts, that's how we're going to describe it. And that's what we'll do in the next video.